Hello everyone. In today's class, we are going to see about fast Fourier transform. We will begin by taking this small example for the first method of your fast Fourier transform, which was your divide and conquer method. And then after that, we'll look into your RADIX-2 decimation in time algorithm. Okay, so we'll get started. So for your divide and conquer method, we have seen in the previous class how to do this by factorizing your sequence length. So here the example, I am taking my sequence length, my input original sequence length to be 15. So I have factorized it into 5 and 3. So the rule set for your divide and conquer method is, if I am writing the horizontal, if I am indexing my inputs horizontally, my outputs get indexed vertically and vice versa. So the previous example I had written in last class was where my inputs were indexed vertically, and here my inputs are indexed horizontally. So that's the only difference. So that was also for sequence 15 point, and it was also factorized into 5 into 3. So let us see how we do this. So we can do it in both ways. It's gonna give you the same output. So I thought I'll just show you this one also before we go to the next fast Fourier transform method, which is the quite popular method used for fast Fourier transform. So what I have here is, I am taking my indexing as 0, 1, 2, 3, 4, 5, 6, 7, 8. So I am indexing it in horizontally, and then I am computing the 5-point DFTs for these horizontal rows. Good. So which means you can see, like for my 3 rows, I have to do my 5-point DFT 3 times, and then I am multiplying with that scalar multiplier W15 to the power of LQ, which, you know, if you have gone through the derivation video for divide and conquer method, you will know. I am taking the output of that to be x0, x1, x2, x3, x4, x5, x6 till x14. And now for these row index sequence, I am doing the 3-point DFT. So I am taking the 3-point DFTs vertically along the columns, as can be seen here. And when I do that, I am going to end up getting your 15-point DFT. And now, since my input was indexed horizontally, my 15-point DFT is indexed vertically, as seen here: x0, x1, x2, right, x3, x4, x5, x6, x7, x8, 9, 10, 11 and 12, 13, 14. So the indexing is vertical. So that is the only thing where you have to be careful, because every divide and conquer method will have a 5-point DFT done 3 times, and it will have a 3-point DFT done 5 times. So it can be, it can be done in 2 ways. The one is where the inputs are indexed horizontally. The other way is where your inputs are indexed vertically. All right. So if you're okay with the indexing, the other parts should not be a problem, and this is what we do. And this is still a very primitive method for divide and conquer method. As you can see, the number of multiplications and the additions that we save by this method is not that much. It's very small, but still, we have to see this method, because this is one of the good methods that we can use if we have to, for implementing your fast Fourier transform. The next method, which is the most popular method, and this is the method I am talking about being used in your FPGA modules, your Texas Instruments boards, and all the DSP processors that are out there in the markets today, work with this RADIX-2 decimation in time fast Fourier transform. And we even have RADIX-4. So what it means is, your RADIX-2 means your input sequence length is a power of 2. So that is what your RADIX-2 means. So if I have a sequence of length 4, and that is 2 to the power of 2, 8, 2 to the power of 3. So all this can come in your RADIX-2 algorithm. And your RADIX-4 is where your input sequence is a power of 4. And then you have RADIX-2 plus RADIX-4. More of, it's using RADIX-2 in some stages, and it is using RADIX-4 for some stages. So that is your RADIX-2 plus RADIX-4. So we will be seeing only the RADIX-2 because that is what is widely used, and it is also what is needed at an undergraduate level. So I am targeting this for undergrad students, and even for your service exams and other entrance and the interview exams, they only focus on your RADIX-2, DIT and DIF algorithm. So when I say DIT, I'm talking about decimation in time, and its counterpart is decimation in frequency, which we'll be seeing next. So we'll be seeing both these. So there are two types of RADIX-2 algorithm, decimation in time RADIX-2 and decimation in frequency RADIX-2. So the decimation in time means you are decomposing your time sequence x of n into your smaller sample sequences, right? Done. That is for decimation in time. And then your fast Fourier transform. So we are calling this as your fast method for Fourier transform because your number of multiplications and additions are vastly reduced. So your computations are reduced, thereby increasing the execution time, or you're speeding up the computation time. Hence it is called as your fast Fourier transform. So the abbreviation is FFT. So to summarize it, now I can write, now I know what these things are, I can write the algorithm that we are going to be discussing today as your RADIX-2 DIT FFT algorithm. Okay, good. So let's get to the core of this. How the RADIX-2 DIT FFT is derived and how it is used to reduce the number of multiplications and additions. So how your DFT can be converted into an FFT. So what we are going to be basically looking at is how your DFT is converted into an FFT using this RADIX-2 decimation in time. Good. So that first step, so we are going to see a 4-step derivation. So we are going to see all the things as your steps, and the first step, and this I'm going to include both the derivation as well as the solution in these steps. So the first 2 steps will be focusing on the derivation, and the last 2 steps will be focusing on how to compute the FFT using these derivation assumptions. So the first thing we are going to do is we are taking my Fourier transform original DFT, which is x of n wn to the power of kn, and I'm splitting that into my even and odd function. Alright, so what it means is I'm taking x of n. So let's say for n equal to 4, I'm going to have 0, 1, 2, 3. Those are the indexing. So I'm going to group them into even and odd. So I'm going to take 0 and 2 and then 1 and 3. That is the first step I'm doing. I'm grouping my even indexes and odd indexes, and then I'm going to have equal numbers. So what is the number? So for n equal to 4, I have 2 even index and 2 odd index. So that is exactly what I'm going to have for here also. For my even x of 2n, I'm going to have this, how many index? I'm going to have n by 2 index. So that is 0 to n by 2 minus 1. And then for my 2n plus 1, I'm going to again have my n by 2 index, 2n minus 1, which is obviously calculated from this n equal to 4 point sequence. And then I can write my Fourier transform in this manner, where my n is getting modified into 2n and 2n plus 1, because it is now an even and odd separated function. So now I go on to simplify this twiddle factor or my matrix transformation W. So I'm going to do the simplification of that, and that is going to give me my first set of equations of my FFT. So this can be written as Wn by 2kn. So I'm going to show it along this class also how we get those, and I've shown it before also how we get that. And for my second simplification, I'm going to write it as 2kn plus k, and that is going to be reduced as Wn 2kn into Wn of k. Alright, good. So now I can write my Wn to the power of 2kn as Wn by 2 to the power of kn. So now my first equation, so this equation is the first stage or the first equation or the first level of your FFT. So I'm taking the even sequence and the odd sequence, so it's gonna be multiplied with Wn by 2 to the power of kn, and then I have a common multiple Wn to the power of k. So the wn to the power of k is not attached to the summation because the summation is for the variable n, and wn to the power of k doesn't have that variable small n, so it is not attached to the summation. So I can write it outside the summation in this manner. So I'm writing it as e of k plus o of k into wn to the power of k. So what does this e of k means? It means my even splitting o of k for my odd sequence indexing and multiplied it with my wn of k. That is your first stage of your FFT, or the first equation that we are going to see. And now this is the decimation in time we have done now, right? That is one level decimation in time, and we are going to decompose. We are going to do this decimation in time further and further till we have to. And how we decide till when we keep splitting? So what happens is, now if I have a 8 point, I'm going to have 4 odd and 4 even. Then I'm going to again further divide that 4 even into 2 even and 2 even, and then odd into again 2 and 2. So 8 will divide into 4 4, then 4 will again divide into 2 2, and again into 2 2. So that, how many times do I have to do that decomposition or your decimation is decided by this formula log 2n. So the log 2n decides how many times you have to do your decomposition. So let us say my log 2n here, it states that it is going to be done for my 3 times. Alright, so I am going to do it for 3 times. So I'm going to have 3 decimation. Okay, so I am going to write, it is going to get easier from now. We don't have to derive it. I have my generalization formula. I can use that. So I know for my first time decimation in time is e of k plus o of k into w and k. And then my second time decomposition is going to be EEK. So that even sequence. So let us say I am having an 8-point sequence. I am taking it as 4 and 4. 4 even and 4 odd, and then I'm re-indexing that even. So that 4 even, I'm re-indexing it as 0 1 2 3, and then which means it will again have my even and odd. So that is my EE of k and EO of k. So that E of k is again split into my even and odd. The same goes for my odd. So I have that 4 odd with me. I'm re-indexing it from 0 to 3. Then it's again going to have even and odd, and that is my OE of k and OO of k. And my wn to the power of k in my second stage decomposition or decimation, it becomes wn by 2 to the power of k. Done. And this is again going, because this is my second stage now, I'm going from my second stage to further one more stage, that is my third stage. And you can easily tell how I've written that third stage or the third level decomposition, because I have taken my EE and it becomes EEE plus EEO. So, and it sounds funny, but yeah, that is how I've written the third time my decomposition. Done. So this is the derivation. So these two steps, the step 1 and step 2, covers the derivation that goes with your RADIX-2 DIT FFT. So I have done that split into even and odd. I am doing it 3 times, and every time I have to index it again, then only this derivation makes sense. But it is easy. It's very this is easier to see and visualize how things are happening inside than writing it with the different other variables. Good. So now let's go to our step 3, and in our step 3 we are gonna see how this is actually executed, how the computation happens in your FFT. So before we do that, we need to see what are this twiddle factors, what are this transformation W, the linear transformation W matrix, and how we simplify it using our periodicity and symmetry property. So we have seen in DFT that your Wn is having this periodicity property, where it becomes from Wn to the power of k plus n is equal to Wnk. That is your periodicity property, and your symmetry property states that Wn of k plus n by 2 is equal to minus Wn of k. Okay, so now we are going to simplify. We are going to use this in our FFT, right? In our stages, and we are going to simplify these twiddle factors, because as you can see, finding anything raised to 5. So if I ask you what is 2 to the power of 5, you may be struggling. You may need a calculator, you may need a pen and paper to come up with that answer. But if I simply ask you what is minus 2 to the power of 1, you will just say it is minus 2. Right, it is something like this. That is why, but it is not integer, it is a complex exponential, but just an analogy I am telling you. So finding even to the power of 5 in terms of complex exponential is very difficult, but the other one on the right hand side is a very simplified thing which we can easily compute. So this is another way of simplifying your DFTs using this property of my W. This we have done even for DFT. We have used a little bit, DFT as a linear transformation where we use these properties and simplify this, but here we again in FFT we are using it. So we are using this in our linear transformation operation. We are doing that in our divide and conquer also. We will be using this, and now we are using this for your FFT also. So in our first level decomposition, I am having right in my first time, what was the equation? E of k plus O of k into W n k. So that W n k means it is W for an 8-point sequence. So that is the example we are going to use throughout, and for my 8-point it is W 8 to the power of k, and that is getting simplified as shown. Now for the second level we'll come to that. The second level decomposition is W n by 2 to the power of k. Right, so that is now written. So I can write it as W n to the power of 2k. Right, I can write it as this. This is my W n to the power of 2k. So my twiddle factors are going to be W8 multiples of 2. So I am writing it as W8 0, 2, 4, 6, 8, 10, 12 and 14. So those are going to be my 8 twiddle factors, and I am going to simplify them using the periodicity and property. So much bigger simplification I can do here. So I can take my bottom row like W8 to 14, and you can easily tell me that I have the periodicity property sitting right there. I can convert that into W80 using my periodicity property. Very straightforward. And then what? I can still think of my symmetry property. Yes, I can think of my symmetry property because my n by 2 is 4, which means my W84 and W86 becomes minus W80 and minus W82. That is the symmetry property I apply to my W84 and my W86. So this becomes minus W80 and my minus W82. That is your symmetry property. Good. So now you see, for my second level decomposition, I have only, what are they? What are the twiddle factors I have? I have plus or minus W80 and I have my plus or minus W82. Right? It is plus or minus W80 and plus or minus W82. That is your second level decomposition. Now for my third level decomposition, I am going to have an 8-point FFT. So my 8-point FFT for my third level decomposition is Wn by 4k, which is equal to Wn to the power of 4k. So it's going to be all multiples of 4. That is for the third stage. EEE of k plus EEO of k into Wn by 4 to the power of k. Remember that funny sounding equation? So that is your third level decomposition. And for that I am taking this W80, W84, W88 and W8 to the power of 12, and that is gonna get simplified again into how the periodicity is going to bring this into W84, 8 and 12. So the bottom row is going to be the same as the top row because of the, not exactly right. So I am getting only these two because my 24 is 3 periodicity. It is having 3 8s in 24, which means it is a 3 period. So that is again W80, and my 28 is having 24 plus 4. So that is going to be W8 to the power of 4. Good. So this is what I have, and I can write my 8 and 12 on top to be also W80 and W84. So that is for periodicity property. And then now can I apply my symmetry property? Yes, my 4 is 0 plus 4, and that is going to become minus W80. So which means for my third level decomposition, my only twiddle factors after simplification and using the property of periodicity and symmetry, I am getting it to be just plus or minus W80. Good? Right, it making sense, right? So see how our first stage decomposition was having what? Plus or minus W80, plus or minus W81, plus or minus W82, and plus or minus W83. Then for my second stage, I was having plus or minus W80 and plus or minus W82. And then for my third stage or the third level decomposition, I'm just having plus or minus W80. So that is pretty much how you simplify, how we have used these properties to simplify this twiddle factors or the linear transformation factor. And now I can this makes computation of my fast Fourier transform lot easier. Yes, so that is now in step 4. What I'm going to show you is I'm going to draw this 3-level decomposition in a diagram or in an illustration, and that is what we call it as a Dit Fft Butterfly Diagram. So this is called as a Dit Fft Butterfly Diagram. So we are going to do that here. So let's quickly see how we do that step 4 here. So I am doing the stage 1 here, right? So the stage 1 is operated with the twiddle factors plus or minus W80, W81, W82 and W83, right? All plus and minus. And the grouping is where it is important. So I am grouping my first, because the first stage is what? You are splitting your signal into even and odd. So I am grouping my even and odd. So I'm taking my first even, that is xe of 0, that is shown by the red blob, and I'm grouping it with my first odd. So I'm grouping it with my first odd, which is my fifth. So what I'm doing is, it will become clear soon, but I'm just telling you this much, that my first 4 are the even and the next 4 are my odd. So I'm grouping it into even and odd. So for my 8 point, I'm going to have my 4 even index, those are my first 4, and my next 4 indexes are the odd. So I am grouping my first even with my first odd, my first second even with my second odd, shown in this blue color, and my third even with the second, right? So that is shown in yellow color, third odd, and my fourth even, which is shown in green color, with my fourth odd. Alright, so that is your stage 1. And in my stage 1, I have this decomposition, and I've used only 4 twiddle factors, right? W80, W81, W82 and W83. So this is my stage. This is the first level decomposition, and let me show you the butterfly diagram, how it looks like for this stage. So we are calling this as the stage 3, or you can call it as stage 1, doesn't matter. Different books you see, going from backward and going in. So this is called as stage 3. So we'll keep it in that way. So this is your butterfly diagram. So I'm just drawing. So always I feel like, after I draw the diagram, writing the equation is a lot more difficult for me. So I write the equations and then I draw these diagrams. So that is your stage 1. And now let's look at the stage 2. So my stage 2 is gonna be splitting this 4 even into even and odd. So that is what I'm shown here. So those pink and blue dots represents my even and odd split up of my even, and then the bottom half, which is my odd, is again split into even and odd. So my indexing is written as E0, E2, right? These are the even index, and E4 and E6. So this index ordering is something you need to remember. So that is coming from bit reversal, but for now I'm just show. So here it is every other sample. So which means my E0 is operated with E2, is paired with E2, and my E4 is paired with E6, and my O1 is paired with O3, and my O5 is paired with O7. So that is your plus or minus W8 0 and W8 2. So for my first pairing, my twiddles are plus or minus W8 0, and for my second pairing, my twiddles are plus or minus W8 2. So for my second stage is the twiddle factors were plus or minus W8 0 and plus or minus W8 2, and you see here how it is being used. Good. And after this equation, now you can draw the butterfly diagram, right? I can draw this butterfly chart after this equation, how it will be from E0 to E2, vice versa, E4 to okay, and then E4 to E6 and O5 to O7. Good. So now coming to the stage 1, right? So let this be our stage 2, and the first one we did was our stage 3. So now we are going to come to our last stage, which is going to have only one twiddle factor, W80 plus or minus W80, and here my pairing is between successive samples. So I am going to take successive samples and then I am going to pair them. I am going to do this twiddle factor plus or minus, then I am going to write the equations here. So let's get to it. Good. So the successive samples are shown in the same color because they are the samples that are getting paired here. So when I pair these samples, what do I get? Yes. So I am going to arrange this in this manner. So that is something. So that is the starting point. So the starting point of my algorithm is what we are writing last. So the starting point of my algorithm is what I'm showing you now. So x0, x4, x2, x6, x1, x5, x3 and x7. So this is the order that we have to follow. Now if we do it in this order, your output is going to be in sequence. So your output transform, your output fast Fourier output transform will be in sequence, meaning it will be x0, x1, x2, x3, x4, x5, x6, x7. So you don't have to do anything at your output end, but at your input you have to do all this, right? x0 plus w80 x4, x0 minus w80 x4, and plus or minus w80 is the format. So x1, x5, then x3 and x7. Alright, so this is how I do my stage 1, because that is why we are calling it as a stage 1, because that is the first stage we are doing after from the input. Then comes the second stage, and then comes the third stage. So these summations equate to that E0, and then on after stage 2 those equate to that xe0, xe1, xe2 and xe3. Good. So this is how you represent your butterfly diagram for your RADIX-2 DIT or decimation in time algorithm. And this is now we will be doing an example. So what happens is you have to write a program. So I'll be showing you the Scilab program for this, and I will also be doing 1 or 2 examples on this to just make sure that you know how to solve this using this method. And then what we will be looking at is we need to see what is the inverse. So this is a forward transform, right? So we are doing the FFT, which is fast Fourier transform, but we also need to compute the inverse fast Fourier transform, which is not so much different from this. It is exactly the same, except your twiddle factors, that W8 we have to use their complex conjugate. So that is the only difference, and then you have a scalar multiple of 1 by n. So we will see that in the coming classes. So for now, I am sure I am sure that you are familiar. You know what is your 8-point RADIX-2, how these Studel factors are computed using simplification, and how we come up with these equations by even odd splitting. Right. So that is enough for today. I'll see you for next class. Thank you.